change in energy in the system. Right. So you know this, that there are three types of energy of a system: kinetic energy, potential energy, internal energy. This is what we are interested in right now. These three. So some definitions before we go ahead. You know the difference between closed system and open system. So first we talk about the closed system, and then we'll go for the open system. So we know that for a closed system, energy may be transferred between such system and surroundings in two different ways. One is the heat, and second is work. There is no other possibility right now. For our case, we'll use this two. The form of energy, the work which we are going to deal with, we'll list it out. Some of them we'll use right now. Some you will encounter in other courses. Right. So we'll assume that heat or energy that flows as a result of temperature difference between the system and surrounding. That's the Q. And it is positive when it is transferred to the system. This is the convention we'll use for our material balance, energy balance calculations. And work or energy that flows in response to any driving force other than temperature difference, such as the force or torque or voltage or other things. So for example, there is a turbine, so the shaft which is rotating because of the work done by the system. So that's called work, the energy transferred in terms of work. And work is positive when surroundings perform work on the system. Right. These two things you have to take care that these are the positive. Then we know that work and heat refers to energy that being transferred, and heat and work cannot be stored. Both are path variable. So when we talk about the energy inside a system, energy content of a system, we don't say that this particular system contains this much heat or this system contains this much work. It cannot be stored. When it is moving from one system to another system, or one system to surroundings, it is called energy or heat or work, that the form of energy. Right. So wait 1 second. Okay. So this is the basic thing. You know this part, right? In thermo and other courses, you must have heard of all. So only convention you remember that Q is positive when enter into the system, and work is positive when work surrounding perform work on the system. Now kinetic energy calculation, you know that EK is given as 1/2 mu square. The unit of kinetic energy is joule. And if there is instead of mass, there is a flow of mass flow rate is given. Then this EK dot is the rate of energy transfer, that is joule per second, or we can say this is equal to watt. And for example, we take a simple system. So remember, we are not going to deal all these things from the point of view of thermodynamics. We'll take care that how it can be useful in taking material balance, energy balance calculation for a system. So let's take in one example of a water which flows into a process unit through pipe with a diameter 2 centimeter at a rate of 2 meter cube per hour. And we want to find out what is the EK dot of this particular stream in joule per second. So here we can simply write that U velocity is equal to, so we have what you can say, volumetric flow rate. So we have V dot is equal to 2.00, and we know it is the circular pipe with a cross section circular with a diameter 2 centimeter. So we can convert that into the cross section area, that is this one. So using that we can find out this is the cross section area. So this is the pi r square. So 1 centimeter square and converted to centimeter to meter. So you got the divided by 3600 to convert hour into second. You got the velocity 1.77 meter per second. So using that you can calculate mass rate is given. Mass flow rate, you can convert it here. So you have water, so you can assume that density is 1000. So 2 into 1000, so you get 2000 divided by 3600. So that is 0.556 kg per second. So you have mass flow rate, you have velocity, so you can calculate the kinetic energy of that stream. So that Ek dot rate of kinetic energy is 0.87 joule per second. So you can see that by rearranging these equations here, you get Newton into meter per second, which is nothing but joule per second, where joule is Newton into meter. Right. So this is the basic thing. Sometimes we need to calculate the kinetic energy of the input streams and kinetic energy of the output streams. So that time we need to know, we need to calculate this much detail. So we need velocities of all the streams which are entering and the mass flow rate. So this is what we have done in the material balance. Okay. Second one is potential energy. So you know EP is equal to mg into z, or if it is a rate, then the mass flow rate is given. So you get the rate of heat transfer, energy transfer, potential energy. So that is EP dot m dot g into z. And the change in the potential energy at two different locations is given by m dot g into z2 minus z1. Right. So we see one example of this. So you have crude oil is pumped at a rate of 15 kg per second at a point 220 meters below the Earth's surface to a point 20 meter above the ground level. Calculate the attendant rate of increase of potential energy. How much potential energy increases? So we want to find out at z equal to below Earth 220 meter to above the ground 20 meters. So we have two values, z1 and z2. You know mass flow rate already given directly kg per second. G you can take 9.8. So you can calculate 15 kg per second, 9.81 meter per second square. This is the conversion factor which we ignore all the time because we know that this is nothing but Newton. And this is the Newton per second, and this is the 20 minus 220. Why they have done this? You understood this part. So we want to find out it is pumped from the ground, below the ground level to above the ground level. So we know that the height is in the initial and final height, the height is increasing. The oil will be pumped from the below surface to above ground level. So the delta Z is positive here. So you can write it that way, or you can take a reference as a ground level, which is 0. Height at a ground level is 0. So your Z2, the final height at which the oil will reach is 20, which is plus 20. And as per the definition, this is minus Z1. So Z1 is below ground level. So that is, as per our reference point, it is minus 200. So 20 minus 220. So that comes to positive 240. So this, you can write it in this way, it's fine. Or you know the logic that whenever the substance location, I mean the height, its initial and final height, its final height is higher than the initial height. So delta Z is positive. And when it's going down, delta Z is negative. So that you can put it accordingly. So when you see positive sign, it means this much amount of energy increased in the system. That's what we have defined. That's based on that, this Z2 minus Z1 is written. And if it is negative, it means its potential energy decreased by that much amount, right? So here you got 35,300 Newton to meter per second, or this much watt, or in the exam, you can simplify this also to 35.3 kilowatt. Right? So that's a better representation. Just final answer only. Huh? No intermediate, you don't need to touch. Okay, so let's go to closed system now. So this is just a definition for EK. Huh? This is for closed system. This is for open system. You understood the difference. Okay, how many of you don't know the difference between open and a closed system? Please confirm now. If you don't know, then I'll explain. Otherwise, I'll go ahead. Siddharth, you know? Siddharth, are you there? Come on, anyone else can give me one sentence answer. What is the difference? Come on, don't be afraid to be wrong if you don't know. That's fine. Yeah, what is the difference between open and closed system? No one?
Sir, in an open system, there is a change of
Yeah,
sir, in
Ishan,
an
go
open
ahead.
system there is change of mass and energy, and
Mhm.
in a closed system there is no change of mass, only energy changes there.
Only energy change. Yeah, okay, good. This is clear for everyone. Good. So you understood that closed system means, okay, you take an example so you remember that way. Take an example of a tea kettle or a water, or you boil the water in a water kettle. So in water kettle, what you do is put the water inside and close it. That's it. You are not going to put water in between, or you're not going to take the water out until it boiled, completely boiled. So that is a closed system in which you are supplying heat, supplying energy in terms of electrical, resistance. So it is heating the water. So you are supplying the energy. So only energy transfer can occur in a closed system. So typically a batch process, you can write it down that a batch process is nothing but a closed system. Batch process means a closed system. So you have a reactor equipment, anything inside, you will feed everything first, and then the process starts. Once the process starts, there will be no mass transfer. Mass transfer will not be there. Only heat can transfer the boundary. So heat transfer, or energy transfer in general, we say, not a heat. Can be any energy. Energy transfer is possible, which is called a closed system. So till now, if you remember all the examples we have done of material balances, do you remember any example of batch process? Any example of closed system? Take any example where the stream data are given in mass, in the quantity, mole or mass, not in flow rate. These are the closed system. We are writing like this, we are drawing a figure like this one, that something enters here, something enters here, something comes out here. We assume that this is continuous, but it's not continuous. If this is given M1, this is given M2, it's a mass. So in that case, we are adding this to, something happens here, and then we'll take it out. It's a batch process. It's a closed system in which something will happen in the process, and at the end of the process, after 1 hour, 2 hour, one day, we'll take out the remaining thing. So that's a batch process. That's a closed system. So one example, if you remember those acid problem, we mix two different types of acid and we get the third acid. It's a batch process. In the same case, if you put this as a mass flow rate, mass flow rate, mass flow rate, it means we are feeding this one at a constant rate, and we are taking something out at a constant rate. So in that case, this mass can enter and leave the system continuously, and that is called open system. So many other examples we have seen are like this. Some examples are like this, which are the batch process. So open processes are continuous or semi-batch, semi-continuous process, and a batch processes are closed process, right? So closed process means we are not changing the mass of the system, only we are changing the energy of the system. And in this case, open system, we'll see in the later. So this is the open system example, where you have mass flow rate, and this is the closed system, where you have only quantity of the system. It can be mass, mole, any of the system. Okay, so let's see the first energy balance for a closed system. We'll simplify it here. So for closed system, you have to write only the box part. Other things, I will give you the slides. So closed system means you are feeding something into it. And at the end of the system, when everything is over, you'll take out something. So input minus output, that must be whatever the change occur into the system. So again, take an example of water kettle. So you are feeding the water inside, close it. So there is no mass transfer now. So now you supply the heat. So the temperature of the water will increase from certain room temperature to say 90 degree. So that delta Q that happen, energy change happen, that is the you provided input from the system, and there is output. There is nothing heat transfer, nothing happening. For example, you have a very nice insulated kettle, so output is zero. In case there is a heat loss from the kettle, so you have some amount of energy is lost to the atmosphere. So input minus output is that one, and accumulation is what remains in the system. That's a simple example. Now we'll elaborate it a little bit. So what we just now talk about is only this internal energy, UF minus UI. That is the temperature change occur. Now, what about other two terms are also important. So our system, entire system we'll talk about. So in the system, we increase the or decrease the internal energy. So temperature increase or decrease. But what about the kinetic energy of the system? So we have to check whether the kettle, is it moving at a constant speed or not? Or it is moving initially started at a 1 meter per second, and then at the end of the process, by the when the you say okay 1 hour, by the end of the process you reach 2 meter per second. So it's accelerating. So it means the initial EKI and final EKI are different. EKF is different. Then you have to find out what is the difference in that. So it means initial velocity of the kettle and final velocity of the kettle. That one thing we have to encounter. You have to include into the system, because it will increase or decrease the total energy of the system. So this we have to calculate. So we need initial velocity of the kettle and final velocity. Next, potential energy. So same thing. Initially at what height it is, and finally the system is at what height. You know the difference in height. If it is going down, potential energy decrease. Going up, potential energy increase. So you need the value of this EPF, EPI. Done. So this two part you have to check for each system. What is the change in the velocity of the system? So you get EK. What is the change in height? EP. Plus we'll see this one. What is the Q supplied to the system, and what is the W work done on the system? These two things will be on the right hand side. This is positive. Right, this is positive because we are assuming that Q which enters into the system is positive, and Q work done on the system is positive. So your final equation is this one, delta U plus delta EK plus delta EP equal to Q plus W. So this you have seen several times in your thermo book, right? So this is what we will start with, and then we'll apply to chemical systems. So what we are interested is simplify the equation, right? Every time what we do, we try to remove the terms, as many as terms we can remove, so that we can simplify the equation and then we can use it. So we'll try to find out that when each of this term can be zero. So we can have those, we look at our problem and see that, okay, this is the case, plus this is the case. So we can make this zero, that zero. The final energy balance equation is this one. This is for closed system only right now. So let's see first one, delta U. So no temperature change, no phase change, and no chemical reaction in a closed system. And pressure is not changing significantly. It's around, less than few atmospheres, around that value, small pressure. Then you can take delta U safely zero. Change in internal energy. We are not talking about the absolute value. The change in internal energy is zero. Same way, delta EK is zero when system is not accelerating. So remember, then delta EK has a relation with velocity. It doesn't mean velocity should be zero. Velocity can be any value, but the initial and final velocity should be same. It remains same. It should not change it during the process. So for closed system, tea kettle, if it is continuously moving at 1 meter per second, you have delta EK is zero. Or if it is most of the time on the table, so it's delta EK is zero. And same way, delta EP is zero when it's not rising or falling. So like water kettle, never goes up and down, right, during the process. So it's delta EP is zero. So well, these two things are interesting because all of our equipment till now we have talked about distillation column, dryer, evaporator, any equipment, they never move. They remain at its location. So delta EK is always zero. Entire system we are talking right now, closed system, not the open system. And delta EP, it's not moving up and down, so also zero. So this is always applicable most of the process equipment in our plant. So this is good. This we reduce this one calculation. Okay. Now let's see Q. So Q is 0 when there is no heat transfer, obviously, right? It means when heat transfer, we'll see next semester, entire course is there on this. So Q, when Q is not 0, when the temperature is difference between the two system and surrounding. So if temperature is exactly same, there will be no heat transfer. Q is 0. That's one possibility. Or the temperature of system and surroundings are different, but the system is perfectly insulated. You don't have any possibility to give the heat outside or to gain the heat from outside. It is completely insulated. Then Q is 0. That time we can put Q equal to those systems, we can put Q equal to 0. So if you see in a problem statement, it's written system is adiabatic or adiabatic process. We put Q equal to 0 in this equation. And when is the W 0? For our case, closed system. Again, this is only for closed system. When there is no moving parts, there is no other work, any other type of work crossing the boundary. That's it. W is 0. So again, we go back same, we see all the unit operations, like distillation, absorption, evaporation. There is no moving parts. I mean, moving part may be internally, but there is nothing work done by the system on the surrounding or other way, vice versa. So most of the time for our all the cases for closed system, this is useful. W is 0, except you have some other moving part like turbine is there, or you are doing agitation, so you are providing work of the rotating. So that all the time we have to encounter this W, how much we are supplying. Right? But most of the unit operations, this one and this one are safe to consider as 0. Delta Ik, delta Ep, and W. So your most of the time equation reduced for closed system is delta U equal to Q. That's it. Okay, so let's see a few examples. So this is actually over-specified problem. We have to calculate actually this Q. We'll see later on how to find out this, but it's given that you have some piston cylinder with a gas inside initially at 25 degrees Celsius. And finally it reaches 100 degrees Celsius and we are supplying Q 2 kilocalorie. Right energy balance for this system. It's a closed system. So we write entire, every time start with this one, energy balance problem, closed system, write this equation always. Delta U, delta Ik, delta Ep, summation is equal to Q plus W. And then find out which terms are 0. So delta Ik 0, delta Ep 0, W is 0. There is no work done right now. So we have only Q equal to delta U, and that is already given here, 2 kilocalorie. So just done some conversion, unit conversion to joule, nothing else. So it's nothing but Q is equal to delta U in principle. In fact, you can calculate this 25 to 100 degree, you know the temperatures. So you can easily calculate what will be the Q required to do this process, right? That we'll see later on. Or if they tell you that 25 degrees is the initial temperature and we are supplying Q is equal to 2 kilocalorie, find out the final temperature. You can calculate that. We need some more additional properties of the gas. Right. So this is the statement. Its internal energy changes 8370 joule or 2 kilocalorie. All are same. They are written in SI units. Okay, let's see another example. So for example, we let the piston move. It's not fixed now. So piston will move and gas will not be released to atmosphere, but gas will carry out some work on the piston. So piston will move. So initial state and final state temperature is same, 100 degrees Celsius, but it is carrying out some work on the piston. So it's moving. So we can write initial equation. Now set all these things 0, which are not considered here. So we can safely say delta Ik 0, delta Ep 0, and W is not 0. So what is 0 here? Temperature is same. Just now we said when the temperature is same, what is 0? So we can safely write here that delta U is 0. It means we are not doing any internal energy change of in the gas. So we can write your formula Q plus W equal to 0. So you got Q is equal to 100. Okay. So this is so it means an additional 100 joule of heat is transferred to the gas, which will nothing will happen. It will just expand. It will give you the work done. That's it. No other change will happen. Okay, so this is the basic thing. So you start with this equation, closed system, put this thing 0. Which one is 0? You have to check delta U, delta U or W or Q, and remaining thing you will get some answer. Okay, now we go back to flow, open system. So open system means you have a continuous flow rate of a system. You have something inlet, something going in, something coming out. So this number of streams entering, it doesn't matter. We have to just make a total of all these things, and whatever number of streams leaving, that you have to make a total, right? That you have to take care. Only thing we will assume here to simplify is steady state. If it is unsteady state, it will add one more factor of time, which we don't want to consider right now. So we'll assume everything is steady state, which means flow rates are constant. They will not change with time. So there are two types of work in an open system. One work is called shaft work, which we have seen previously in a closed system, something moving part, which is called WS dot. And now each stream which is entering in the system and leaving the system, it will also carry the flow work, because the pressure, temperature, volume of flow rate of each stream is different at inlet and at outlet conditions. So we can write here two things here. The shaft work is anything which is done by the system or on the system due to moving parts. So you have pump or rotor or turbines. So if you see an example where they say that something is moving and work done by the system is this much, or work done on the system is this much, then for open system, you have to write WS is that much, not the W. W now is divided into two parts for open system. And the flow work is the net change in the inlet and outlet condition. So the rate of work done on the fluid at the system inlet minus rate of the work done by the fluid at the system outlet. So how to calculate this flow work? So the flow work is nothing but, take an example of say one inlet and one outlet, and conditions are given. So flow work is nothing but P into V dot, and outlet is P into V dot. And the difference between these two, we can write it is the flow work, is the inlet minus outlet. That will give you how much is the flow work. So this will be positive. It means work done in the system. Inlet is more, outlet is less. So that much work is done on the system, flow work. So we can write all together here, W is equal to shaft work separately. We can find out this data which is given. And plus this we can calculate from the flow rate, volumetric flow rate and pressure conditions of inlet and outlet. So like I said, if you have n number of streams, make a summation here of all inlets minus n number of streams which are leaving, which will be here. Okay, so let me know if you have any doubt here. Closed system, we have only W, Q plus W. That's it. W is a shaft work. There is no mass leaving or entering, so there is no work done because of that. But open system, there is some streams are entering and some streams are leaving. We'll also do some work on the system. Its flow rate and pressures are different at inlet and outlet condition. In case this is exactly same, this and this are same, then there is no difference in this, so flow work is 0. It is possible. So that you have to calculate. Okay. Before we go ahead, some more revision of the properties, right? You remember extensive and intensive property. Extensive property means those depends on the quantity of the system, quantity of the material which you consider. For example, mass, mole, volume, kinetic energy, potential energy, internal energy, all are extensive property. And intensive property means they don't depend on the quantity of the system, like temperature, pressure, density, and all those. And plus we define another set of properties which we'll use frequently now is specific property. So specific property is an intensive property, intensive quantity. We can obtain it by dividing an extensive property by the total amount of the system. So total amount of the process material or flow rate. This is very useful especially when you are doing the scale up, scale down, when you are doing, it's better to represent something in terms of a specific property instead of extensive property. We'll see some examples so you get the idea. So, for example, the volume of a fluid is 200 centimeter cube and mass of the fluid is 200 gram. So instead of writing these two things, you can write simply that specific volume of this particular fluid is 1 centimeter cube per gram. That is a better representation. You take any scale, you do this, you take the fluid this at a lab scale or an industrial scale, it will specific volume remain same. It will not change for given process conditions. That is useful property. Similarly, if you have flow rate, so your mass flow rate is 100 kg per minute and volumetric flow rate of that is 100 liter per minute. So we can simply find out the specific property is 100 liter per minute divided by 100 kg per minute is 1.5 liter per kg. So you can see that some of the properties like here, what is this one? Centimeter cube per gram or liter per kg is nothing but specific volume. So that we can find out for a system, for example, for this particular stream, we can easily find out by taking the appropriate ratio. So it's a density or this is density. So even this density you can easily find out from either a closed system, like this is the mass is given, or from a flow system, open system, where the flow rate is given. Okay, so that we apply for energy now, which is useful again. So, for example, if the rate at which kinetic energy is transported by a stream is 300 joule per minute, and its flow rate is 100 kg per minute. You got idea? This we calculated. For example, we did previous example, kinetic energy calculation, 1.5 mu square. So we know velocity, we find out this one somehow. So we got the Ek dot 300 joule per minute. And we know the mass flow rate of that particular stream is 100 kg per minute. So well, this two information is interesting as long as this process, this particular stream remain as it is in the same temperature, pressure, everything conditions, its specific kinetic energy will remain same. It will be 3 joule per kg always. So that's why if you again refer steam table and see the enthalpy, entropy, all the data given are not absolute value. They are all are specific value. It can be per mass, like this one, 3 joule per kg, or it can be joule per kilomole or something like that. So it can be per mole or per kg, any of the units. So that you have to take care, because in energy balance, many of the steam table, they represent per mole data or any of the energy, enthalpy, internal energy, entropy and other data are given per mole, and sometimes some data are given per kg. So you have to make sure you are using the correct specific property. So you use per kg data, and when you're converting that, you make sure you multiply by the mass or mass flow rate. And if you're using molar property, make sure you multiply with the appropriate mole or molar flow rate to get the energy or rate of energy. Okay, so for example, you have a specific energy, right? U cap, for example, somehow you get this data. So what you do is multiply by its mass of the system. So you get the U in joule for that system. Or you have a U cap. This is remain same for the system. And then you know that particular stream's mass flow rate is given. So you will get U dot, which is joule per second. So this is the data. You will get it from table, which is same for given temperature, pressure, and type of the fluid. Only thing is, depending on the closed system, you have this. Open system, you have flow rate. Now, apart from internal energy, for open system, they have defined one more type of property, which is called enthalpy. And you know the definition of enthalpy is H cap is equal to U cap plus P into V cap. So this what they have done actually is that flow work. If you just now you have seen in previous slide, right? Shaft work and a flow work. So flow work is nothing but just PV. And the other U cap is the internal energy. So they combine this two and defined as a new property. It's easier to handle. So that's enthalpy. We'll use this one frequently. Whenever you see open system, it's easier to use. enthalpy instead of using flow work separately and U separately. Okay, let's see an example here. Okay. So this from the reference book, in case you want to refer again. So we start what is given here. The specific internal energy of helium is 300 Kelvin. 1 atmosphere is this much. So this is the data, right? So like I said, you know the component, you know temperature, you know pressure, you can find out this easily. So this is C. This is specific internal energy, but it is per mole, not kilomole. Huh? This is joule per mole. And the specific molar volume at this condition is this much. So this is the molar volume. So previously we have seen a specific volume where the volume is given in say meter cube per kg, or in for example in liter per kg. So those are the specific volume per mass, and this is the specific molar volume to be specific. So here you have 24.63 liter per mole. Right. So this much data. These are the data. So if you know temperature, pressure, this and this you can get it from somewhere. It's available for most of the components, or you can estimate it from some equation. Okay, now the question is calculate the specific enthalpy of helium at this temperature and pressure. That's the first question. Second, the rate at which enthalpy is transported by the stream of helium at this temperature, same temperature and pressure, if its molar flow rate is this much. So two calculations you have to do. One is this specific enthalpy calculation. So we'll note it down, that is H cap. And a second is you want to find out what is the rate at which enthalpy is transported. So you want to find out H dot of that particular stream, right? The rate at which. So we'll write the equations which we know. So enthalpy only you want to calculate here. So H cap is equal to U cap plus PV. So U cap is here, pressure is 1, and V cap of this system is this much, 24.63. So again, we go back to the first chapter. When we try to add two terms, their units must be same. It must be dimensionally homogeneous. So it is dimensionally, it is homogeneous. Dimensions are same, but units are not same. Here it is joule per mole. Here it is atmosphere liter per mole. So this unit must be joule per mole. It cannot be different than that. Otherwise, you cannot add them. So to just unit conversion, you have to convert this atmosphere liter per mole into joule per mole. So in the reference book, they have given a nice trick. Is this one. You know the R, gas constant R. R is 8.314. In terms of joule unit is 8.314 joule per mole Kelvin. And that is also equal to, in terms of liter atmosphere per mole Kelvin, is 0.08206. They both are equal. So this is what we need actually. So they have used this data and converted that in terms of a conversion factor. So you can use it to convert this liter per mole and joule relation. So they have used this one to find out liter into atmosphere, joule per liter into atmosphere. So where mole will be, mole remain because we need mole here. So we need joule here. So this liter into atmosphere per mole, this is the unit here. And then we have conversion factor between joule and liter atmosphere is this one. This we derived from here, right? So this is just a conversion factor, which you can remember this way, that 103.1, 101.3 joule per liter atmosphere is the conversion factor. So you multiply it here, so liter atmosphere cancel, you got joule per mole here, joule per mole here. So now we can add numeric value, which gives you 6295 joule per mole, which is the first answer, specific enthalpy. Now second part is specific enthalpy is known and the flow rate is given, molar flow rate is given. So molar flow rate means N dot. N dot is 250 kilomole per hour. Now this is kilomole and this is mole. So you have to convert any one of them. They have not asked which units you keep it, but any units you like. So you convert any one of them and then you can multiply them. So you get the final answer in joule per hour. Or to be specific, you can keep it in joule per second, which is in terms of watt. So we can just simply multiply here that N dot multiply by H cap. So N dot is 250 kilomole multiplied by 1000, so mole per hour. So you get final answer in joule per hour, and still you can convert into joule per second. And when the answers are in like this 10 raised to 9, you can either represent in scientific format like this, 2 decimal points, and scientific format, or convert into kilowatt or megawatt or gigawatt in that representation with a numerical value representable. So we have seen energy balance for closed system and open system. Only difference is in closed system you have W, in open system you have W is equal to Ws plus Wfl, flow work. And to include that flow work in the calculation, to simplify it, we are defining new property, that is the enthalpy. So using this enthalpy, we'll write energy balance for open system now. You don't need to write everything here, what I show. Main equations you can remember, other slides are available. So open system steady state. So we can write easily input equal to output. So here we know that the output streams are this many, whatever the number of streams, their energy is this minus energy of the input stream. The difference in that energy is nothing but the flow, heat energy flow to the system Q dot plus W dot S. So now you see here, we replace this W with Ws dot plus W dot FL. And W dot FL goes other side and combined with U cap and becomes H cap on both the sides. So now you have the final simpler equation is this one, where m dot they have taken out common. So again, remember that we are assuming that all the cap, this all H cap are given in per kg unit. So that's why we are multiplying by m dot j. Otherwise, you cannot take it out as a common here. And then this you have Q dot plus Ws. So this is only shaft work on this side now. So simplifying this equation, you can simply write this minus this is delta H. This and this term is delta Ek dot. And last this and this is delta Ep dot. And right side you have Q dot plus Ws. So this is the final equation for open system steady state. Delta H dot plus delta Ek dot plus delta Ep dot equal to Q dot plus Ws dot. So dot means it's a flow. It's not. It's a rate of change of the energy, not the only joule. It is joule per second each term, or any appropriate unit energy per time. Okay, so we know other terms. We know that this is delta Ek. So delta H is nothing but this one, right? This minus this. So all the output streams enthalpy, total enthalpy, rate of change of enthalpy, and minus enthalpy of inlet streams. And delta Ek and delta Ep, we will set it to 0 obviously, but we'll start with verify it that delta Ek inlet, outlet minus inlet, the difference is how much, and similarly delta Ep dot outlet minus inlet is how much. Any doubt up to here? I'll give you a minute to think. See, we will only mostly we are interested in this and this. Okay, we will not have a reactor which is running around, and will not have a distillation column which is going up and down. And other than the turbine or other this kind of cases, we'll have shaft work also, mostly 0. So what we are interested in, only one property is enthalpy here. So we need enthalpy, enthalpy, enthalpy. That's it. Specific enthalpy to be specific again. And then use that specific enthalpy to find out the total enthalpy, and then take the difference, find out delta H, and find out the Q. Okay, let's see an example here. Simple. Just have a look. Don't do any calculation here. So what we have here is that 500 kg per hour of steam. So steam is using to turn the turbine, right? So it's inside is a turbine. And then steam enters the turbine at 44 atmospheric pressure, very high, and 450 degrees Celsius. Okay, one homework. What is this steam? Which phase it is in? Is it saturated steam or a mixture of steam, water, and liquid? How much water, how much liquid? You can find out. And the velocity is 60 meter per second. Well, so the pipe diameter is something given, then you can calculate. Here it is given directly. It enters 5 meter below the turbine inlet, and at atmospheric pressure, it leaves at a point 5 meter below the turbine inlet at atmospheric pressure 1 atmosphere and velocity of 360 meter per second. And turbine delivers the shaft work of 70, so it's going out of the system, so minus 70. And the heat loss from the turbine is 10⁻⁴ kilocalorie per hour, so minus 10⁻⁴. So now you have to take care of this. Read the problem, see what is done by the system or on the system. So here the system is delivering the work outside, so that is minus 70, and heat is lost to the surrounding, so minus 10⁻⁴ kilocalorie. So you understood now. So you have a P here, you have, this is the mass flow rate. So mass flow rate you can convert into V dot here, that we have if we need this data. Similarly, this also is given here, mass flow rate, and you have pressure here. So we'll use this information to do the calculation. So we'll start with full equation, just rearrange it. Delta H is equal to Q plus Ws minus Ek minus Ep. So we will verify this, how much it is. We don't assume 0 because they have given some information here. And especially when you see the difference here, this one and this one. So it's better, no, you cannot ignore it. We have to, you have to calculate it. How much it is, we'll compare. So first thing, mass flow rate, 500 kg per hour, kg per second. So first calculation, delta Ek. So it's nothing but 1/2 U2 square minus U1 square. So this is given 360 minus 60 square. Mass flow rate is this. Others are just conversion factor. So you get 8.75 kilowatt. Similarly, delta Ep, Z2 minus Z1. So again, this is going down. So Z2 is minus 5. And your original point is say 0. You take a reference point, is 0. So that is minus 5. So you simply write delta Z. Okay, you don't forget about the Z2 and Z1. You can simply, in our case, you can assume that, okay, this is going down. So your difference in height is negative. That is minus 5.